Yeah, well, thanks, Paul. Thanks, everybody, for having me. So let me just start out. I am a civilian employee at the Naval Academy. I just want to clarify exactly as you're thinking about me. I teach physics and astrophysics to midshipmen who will become officers in the Navy. And I'm also obviously an astronomer. So my daytime job really most of the time is teaching, but as much as I can put the time into the research and in the summers, I'm absolutely still very much a scientist. And I am required to give you this disclaimer at the top of the screen that the views that I will be expressing are clearly my own, and they are not reflective of the Naval Academy or the US government, etc. So with that out of the way, thank you very much for having me. I'm going to talk about what I consider the surprising value of comet morphology. And as you'll see through the talk, what I mean by that is that I think most professional astronomers today sort of discount morphology as not necessarily the cutting edge of comet science, but nonetheless, I think it's very valuable and it certainly has its place. And I think it's something that is applicable to many of you. You have the capabilities to be able to do some things that would be very interesting, especially I'll say as I was watching these announcements and some of the deep imaging that got taken, like the 226 hours. Boy, that's some fantastic imaging I'd love to see turned into comets. All right, so first thing I want to say is that when you see beautiful pictures of a comet like this, you probably already know this, but that's probably not coming from a professional astronomer. Usually when we are firing our large telescopes on them, we have tiny fields of view. So the three smaller figures here are pictures I took of the same comet as that spectacular picture on the left, looking much less impressive. But these do allow us to learn things about the composition and the behavior of the comet, and in particular of the nucleus at the heart of it. And I'll get into what all that means in a moment, but just kind of want to set your expectations that in general, when I'm talking about a comet, I'm talking about this zoomed in, teensy little bit, very small field of view right near the brightest part of the image. So here's a quick outline of my talk, give a little bit of background and motivation, in particular, why are we interested in studying comets and asteroids, talk a little bit through some of the results that the heart of this is comet morphology, things that are current right now, some advances that I have made and the field is making right now. And then at the end, as I said in my abstract, I'm going to talk a little bit about ways you might be able to try this on your own if you're motivated to do so. So first off, with the background, I presume everybody on here is at least familiar with what a comet is. Hopefully you've all seen one with your naked eye, but if you haven't, typically every 5 to 10 years, a bright one comes around. And we have not had any really great Northern Hemisphere ones in a while, but stick around, there will certainly be a bright one that will come that you'll get to see with your eye before long. But in general, we talk about comets having several basic parts. So at the core of it is the nucleus. This is a small body, rocky, icy, dusty, which is the heart of the comet. As that the ices there are heated by the sun, they sublimate and they release, they drag dust off of the surface and they release gas as well. And so that dust and gas around it, we call the coma, and then extending out behind it a good ways, and what we normally recognize with our eye is the tail. Rarely do we see a very clear gas and dust tail as shown in this image. It's more often that they're largely overlapping and we just say tail. Just to throw some numbers in here, the nucleus is typically smaller than 10 kilometers. Coma is sort of 100,000 kilometer scale, and the dust tail can extend for 1 million kilometers or more. So every once in a while, you'll see a news story about a comet bigger than the sun, and that's referring to what is the measurable extent of the dust tail. One of the exciting things, and I'll get another slide coming up in a few minutes, with comets is that we have actually been able to image directly via space missions up close the nucleus of a comet. And this is one of them from the Rosetta mission about 10 years ago. What I like to show is this version of it, though, where it's actually overlaid to scale with the city of Los Angeles. And I think that is a helpful way to visualize that. So often in astronomy, we're talking about things that are just unimaginably large. But a comet is something that we could, if we landed on it, we could go and just walk around it in a day or so. You could traverse this thing on foot. Gravity might be an issue, but you get the idea here. So these are very tiny little things that are left over from the formation of the solar system that we're trying to study. I mentioned the comets are sort of rocky and dusty or icy. Depending on who you talk to, they might describe it different ways. But the basic idea was developed around 1950 by Fred Whipple, who's shown in that left image. And for decades, astronomers have called them dirty snowballs, although I think today the consensus is more icy dirt ball. And it's kind of just semantics. But the idea there is that they're frozen gases as well as dust intermixed inside the comet. And as I said, these are of interest, comets are of interest in trying to help us to understand how the solar system formed. So in summary, I would say that comets are leftovers of planet formation. So early in the solar system, the sun was probably a disk, and things coalesced into the planets that we know today. But there were leftovers, things that weren't incorporated, and those generally became comets and asteroids. So comets and asteroids, by studying them today, are telling us about what the situation was like early on in the solar system. And we know that this process is likely ubiquitous because we can look at other young stellar systems and we can see what we call protoplanetary disks, we as astronomers. This is not what I do, but what astronomers do. So we see these things. In particular, we can see them when we have extraordinarily good spatial resolution at long wavelengths, at radio and millimeter wavelengths. So the Lowell Observatory in Chile, in particular, has just been groundbreaking for being able to deliver just incredible pictures like you see here. And probably most of these gaps harbor planets, and they're in the process of forming, much like our solar system was shortly after the sun contracted down to turn on to become a sun. Sort of a cross-sectional sketch of what one of those protoplanetary disks might look like is shown here with the sun on the left. Closer into the sun, where it's going to be hottest, is where the least volatile things, your metals, for instance, and rocks are going to start forming out, the things that form into rocks. That's where our terrestrial planets formed. And then as you go further out, you'll get to what astronomers will call a snow line, meaning in particular where water ice is going to form, where the conditions are cold enough that water ice can form, but not just necessarily water ice, also ices of other volatiles. In particular, comets are made out of carbon dioxide and carbon monoxide, as well as water. And so there would be a snow line for each one of those species. That snow line also, as is kind of illustrated by the white dashed line here, bulges out the further out you go because you have some optical depth effects where there's enough material along the line of sight that the temperature cools down and the ice is able to form in more places, not just in the plane, but also off the plane. So anyway, this is all just background of we're trying to understand what this was like for our solar system when the sun and the planets formed. And comets are probably the best, certainly the most accessible, largely unprocessed remnants of that. So that's why we are so keen to study them today. So currently our solar system, if you first take a look at the top part of the graphic here, the remnants of that disk where the planets formed is still evident because all of our planets are still basically in that same plane. If you go out beyond Neptune, you get the region called the Kuiper Belt, where Pluto and many thousands of other objects still reside today, and that's still largely in the plane of the solar system. They do start to get a bit of an inclination, so there is some puffing out there, but not a whole lot. But if you were to take all of that and zoom it in just to the middle pixel or so of this small figure, or of the bottom figure here, and this small center point there is all of the solar system that we mostly think about. And then out beyond it is this thing called the Oort cloud, which is the things that are just barely gravitationally bound to our sun, extending out to almost a light year away. And that is where most comets probably reside for most of their lifetime. So most of the comets formed much closer into the sun, but they were gravitationally kicked out to these very large distances. They have, through various processes, been scattered into essentially a cloud that's in all directions around the sun. And every once in a while, one of those will get perturbed and make its way back into the inner solar system. And when that does, it will often appear as a bright comet, or as a comet, sometimes bright. So I just kind of want to make these ties to help you to understand where things are coming from as they're making their way, where they've been stored for so long, as they make their way into the solar system where we can study them today. As I mentioned a few minutes ago, we have been able to visit several comets with spacecraft. The 6 comets that we have imaging from are shown here. These have all happened in the last 40 years or so. The most recent one was in the third upper row, middle panel, 67P Churyumov-Gerasimenko, which was over 10 years ago now that we first visited it. And at the moment, there isn't any mission currently flying to a comet, but we do have the Comet Interceptor mission, which I'm a part of, that is scheduled to launch in 2028 or 2029, and will hopefully make the first flyby of one of those comets coming from the Oort cloud. So every other comet that's been visited has been on what we call a short period orbit. So it is a much more predictable orbit that we know every few years this comet will come around. Halley's every 75, but the others were all under 10-year orbital periods. But we've never visited one that's coming directly from the Oort cloud. So we're very much hoping that that will work out with Comet Interceptor. I'm happy to talk more about that after the talk. But comets, visiting a comet with a spacecraft is of course very, very expensive. It's time consuming. So it's not feasible to visit every comet in the solar system. So we have to find other ways to do it much more cheaply, which is where the things that I normally do come in. Remote observing, or observing objects from the ground, or potentially from the atmosphere, above our atmosphere, but still close to Earth with a space telescope. So this is a figure that I love to show when I'm teaching astrophysics to midshipmen, because it shows the whole range of the electromagnetic spectrum. So the shortest wavelength things are on the left-hand side of the plot. The longest wavelength things are at the right. So over on the left, you've got things like gamma rays and X-rays and ultraviolet. On the right, you've got things like radio waves. And in the middle, where you see the rainbow, is the visible spectrum, what our eyes are sensitive to. But what you also see shown here, and is plotted on the y-axis, is the what's labeled here as atmospheric opacity. So the yellow part, or the gold part of the plot. And so when the opacity is at 100%, what that's saying is our atmosphere doesn't allow light in. And that's a very good thing for us to be able to live here on Earth. We certainly wouldn't want gamma rays and X-rays and UV rays penetrating the atmosphere. But as an astronomer, it's frustrating because there's lots of really interesting things going on at places where we can't observe from the ground. So there are a few windows where we can, obviously the visible part of the spectrum, the radio part of the spectrum, and a few parts of the infrared. But everywhere else, if we want to study them, we have to go up into space. And I've noted across the top in these 3 yellow or gold boxes where the particular atoms or molecules that are of interest to comets are observable. So the things that I would argue are most interesting in a comet are what are called the parent molecules. That's the water, carbon dioxide, carbon monoxide in particular, but also many more complex species as well, carbon-bearing species. All of those, or most of those, are only visible at wavelengths longer than visible wavelength, and quite often not visible through our atmosphere from the ground, especially the water, CO, and CO2, because we have water, CO, and CO2 in our atmosphere, and it's difficult to see through those same molecules. If you're interested in the atomic species, so if you wanted to make comparisons of the composition at the most basic level, measuring individual atoms of hydrogen or carbon or oxygen, you'd have to get to ultraviolet and shorter wavelengths, which again, we can't do from the ground. So what we're left with is what comet scientists call daughter radicals, and that's largely what I'll be talking about today. These are things that are produced generally by photodissociation of more complicated molecules, and they are, so things like OH, so a water molecule were hit by the right wavelength, sunlight would produce an OH radical as well as an H, a hydrogen atom. And so just by coincidence, most of the most common radicals that are observable at visible wavelengths. And so that's largely what I'll be focusing on today and what we've been able to learn from making those studies. But as I said at the beginning, morphology is just one part of the way we study comets, and arguably the least sexy of the ways that we do it these days. Photometry, that is the measuring of the light, is quite prevalent, and that has become, I think, much more prevalent recently as we've had the computational power and the automation where, for instance, I'm part of a team where basically every comet that's observable gets observed as frequently as we can, and there's a pipeline that's run on it and just automatically finds the comet and measures how bright it is. And then it gets tracked, and you can make a figure like what's shown here, where you can see how it behaves over long periods of time. You can see it doing weird things like an outburst, which are the things that are flagged with the red arrows in that figure. So I think photometry is really popular these days because of technological advances. But really where I think most astronomers would tell you the value with studying comets is in spectroscopy. So splitting up the light as a function of wavelength and then figuring out what it's made out of. This is a nice composite image from a review paper in a book that just came out a couple of years ago. The chapter is freely available on arXiv. And it shows where the various bright lines in comets typically are the most interesting lines of comet molecules are detectable. So they're all over the place, but they are especially in the infrared. And then, as I said, that leaves us with morphology, which is what I'm talking about today. So let's move on to that. One thing that I really love about what I do, and this is one of the things that really appealed to me when I first got into astronomy in graduate school or thinking about a career, was this idea that comets are things that humans have been observing for centuries, millennia even. And every once in a while, a bright one comes around that just captures everyone's attention. And I love that that I can talk to my mom about what I do. She can tell her friends about what I do. I run into somebody on an airplane who might have heard about something that I've been involved with, or a cab driver. And I think that's a lot of fun. So just to kind of trace some of this ancient history of comet morphology, I'm just fascinated by this Chinese silk shown in the upper left, where there were a couple of dozen convincing drawings of comets. The silk itself is about 2,000 years old, but given the frequency of really bright comets, they were almost certainly recording these things for decades, if not centuries, before that silk got made. And then you've got the Bayeux Tapestry shown in the upper right, which was made around the year 1100, showing the apparition of Halley's Comet coming through. So that it's sort of in the upper middle picture, people are pointing up towards it there. And then, of course, Newton, when he was coming up with his theory of gravity, the first real test he made of it was calculating an orbit of a comet to show that a comet that had been seen on one side of the sun and then a new comet came out later was actually the same comet, and it was following an elliptical orbit around the sun. So I don't think I need to convince you anymore that comets, the shapes or the morphology of comets have been studied and been aware. People have been aware of them for probably as long as people have been looking up at the sky. In more recent times, another bit of value that comets offer is in actually telling us about what is going on with the sun. So my thesis work was studying so-called sun-grazing comets. And so these are a few images from a while ago now, but showing different ways that studying the comet itself as it's close to the sun gives a sort of a test particle of what's happening near the sun. So in the animation in the upper left, you see Comet Encke getting hit by a coronal mass ejection, and the tail, Encke's tail, got separated and kind of floats away off to the left of our picture. And so that was really interesting to the solar physicists because they now could make some measurements about how strong that CME was and know exactly where it went, because we knew in 3D right where that comet was. Another one that was interesting was a sun-grazing comet called 2011 W3 Lovejoy in 2011. As it passed close to the sun, and the tail, what we saw was that the ions in the tail followed magnetic field lines. And depending on the direction of the magnetic field lines, sometimes the tail ions went up from our point of view, sometimes they went down, which is why you see this kind of wiggly shape here. But again, that was just fantastic for the solar physicist to be able to have real data to use with their models of what the magnetic field lines were doing at the time. And then to quickly summarize sort of the biggest, what I view as the biggest developments in comet morphology in the second half of the 20th century, was the helping to enable Fred Whipple's idea that comets were ice, made out of ice, especially water ice. The water or the gases respond differently to solar radiation pressure than dust, that we can now trace that dust particles are following a trajectory that's different, that's affected by what we call non-gravitational forces from sunlight impinging upon them. And in general, the gas does not exhibit that. And in the 1970s, some developments were made to try and isolate particular gases. These were done largely led by Mike Ahern at the University of Maryland, who happened to be my PhD supervisor. So you can sort of start to see why I might be interested in this. But then the current technology for this was updated in the 1990s, and that's what we're still using today. And it was Mike Ahern was still involved with it, but it was led by some of his colleagues and former students, which was published in this paper by Farnham et al. 2000. And I'll get back to this in a few minutes, but those filters still exist, but they are not available to many places now. And so that's one of the things I've been working on, is to get more of these filters available to myself and to the community. All right, so I want to spend a moment here talking about why we use these narrowband filters. And depending on how familiar you are with filters and with thinking about spectra, this might make sense, or if it doesn't, if there's too much material in here, feel free to ask me more about it later on. So the top figure here shows a high resolution comet spectrum. That's the black line, and it's overlaid with six common filters from I think it's the Sloan Digital Sky Survey set. So they're standard filters that you can buy, and they are wonderful for instance, measuring colors of a star and figuring out what its spectral classification is. And that's what these filters were sort of designed to do. But if you wanted to study a comet, what you'd see is that any given filter, and just look where the color overlaps with the black, most of these filters are going to have a lot of gas or different gases in them. And there's also a lot of parts where there's no gas, which comet scientists will call continuum, because at those wavelengths, the only brightness that we'll see is going to be sunlight reflecting off of dust. So if you're trying to characterize the comet in the same way that we make the spectra of stars, it doesn't work very well with the common filters. But the narrowband filters, which are now shown in the bottom panel, are much, much better for this, because they were designed to specifically isolate with very narrow filters, typically about 6 nanometers wide, very small portions of the electromagnetic spectrum that were centered on the bright emission lines that are visible from the ground in comets, from these daughter radicals. And then there are also 4 filters, which are the ones that are colored on the bottom here, that were at regions where there was known to not be any strong emission, and we call those continuum. So those are places where we can sample the dust, and we know unambiguously we have all dust in our image. And by carefully using these filters, we can then make images of bits largely just of that particular gas that is of interest to us. There's a bit of extra processing that has to go on, but largely we can take a picture and know that in that picture, the only thing I'm seeing is, for instance, CN or OH. But that's not all. In order to really learn what's going on, it also requires some additional processing. So the first image here shows what a plane image or what an image I just took using that CN filter looked like straight out of a telescope. And I want to point out briefly here, and I'll come back to this. This was taken from what's called the Hopper Hall telescope, which is at the Naval Academy. So this is sitting here literally right at sea level in Annapolis. I mean, it's on top of a 5-story building, so it's maybe 20 meters above sea level, but it's in downtown Annapolis. I have to deal with lights from the state capitol, lights from the football stadium. But I can take images, decent quality science images there. So anyway, that first image is what it looked like straight out of the telescope. It's centered on the comet here. The comet looks kind of fuzzy. If you see some straight lines, dashes, those are stars that trailed through during the exposure, which was probably, I forget, this was probably like 3-minute exposures, and maybe 3 to 5 of them that I combined is my guess about that one. And then I run some code on it to calculate the average or median brightness at a particular distance from the brightest portion. That's that model shown in the middle. And then I remove it. I either subtract or divide it away. And what's left over on the right-hand image is just the parts that are different from that smooth brightness profile. So what I've done is I've really tossed 90% or more of the light, and I'm just looking at that last few percent signal that is not symmetric. And we've learned that signal is often diagnostic of what's going on in the nucleus, and it will often change with time and let us learn about that tiny little nucleus, which is smaller than a pixel in any one of these images I'm showing. But we can learn about what's going on there. And just to help you visualize this better, this is a different comet, but here's a nice animation of one that we published in 2011, where you can see the comet, and so the parts that are of interest are the brighter parts here. So the comet would be centered, the nucleus would be the center of this. And what it appears to be doing is to be rotating around with a period of around 18 hours at this point. And there's just apparently one gas jet that seems to turn on, and as it moves around, you see that jet expanding outwards, kind of like a sprinkler in your yard as it sprays water and turns around in a circle. And so again, we were able to figure out what the rotation period of this comet was, and you can start doing some more math about the comet once you start honing in on the period and some other things. Another example was one from a paper we published in 2018, although I think the data were collected 2008, as I recall, or 2009, as I recall. This one now, it's a different color scheme here. Red is the bright, red and orange, and the blue and black are the faint. So the red parts are where there's excess gas. And here, this looks like there are two jets. It appears to have material leaving the surface from two different places. And they're kind of making a corkscrew as the comet rotates around, and they spiral outwards down towards the lower right and out towards the upper left. And again, this was one where we determined the rotation period. We also were able to do some really complex modeling to figure out where on the surface these would have to be. It turned out that in this case, one of these jets was staying on even when it should have been in the dark. And so we hypothesized in this case that it was probably active due to something more volatile than water ice, so probably carbon monoxide or carbon dioxide. So again, sort of a breakthrough that we were able to do with that just from looking at the morphology. So I'll pause briefly from talking about comets to talk about asteroids as a setup for why the rotation periods in particular are of interest to me for comets. So with asteroids, you don't have to deal with gas. Asteroid is just a rock and it's inert. So wherever you observe it, you're able to take a picture, and you know any light you see is just reflected off the surface. And as you do that, you see the asteroid get brighter and fainter and brighter and fainter, and you can figure out how fast it's rotating as a result. And you can also figure out how big it is quite easily that way. And what the asteroid community learned by doing this on hundreds and thousands of asteroids was that there was something called a spin barrier shown in this image. And what they eventually realized was that most asteroids, anything larger than sort of about 100 meters in size, was not a solid object. That larger than that, they were what we call rubble piles. Literally, it's just piles of rock that are held together with nothing really more than gravity. And that as soon as you spin them up faster than a certain speed, they start to lose material. That idea was developed before we'd had any missions to things of that size, but then as soon as missions went there, they looked exactly like the models had predicted they should. So we have no doubt that small asteroids are rubble piles. The comet community, though, has not been able to get anywhere near that much data because it's very hard to measure the nucleus of a comet. You can do it when they are very far from the sun, but then they're very faint, and few or if any telescopes are able to do it. So we've been able to measure it for, at this point, rotation periods of several dozen comets and radii, or what we call effective radii, of about that many as well. Here's a plot, again, from my chapter now in that book I mentioned, Comets 3, which, again, the chapter is available on archive. And we are very far from having a convincing picture, but it appears that there's this region shown by the dashed line here, below which very few, if any, comets exist. And so from that, we have inferred that comets must have some internal strength, and they also must have very low densities. And that was predicted before we'd sent any missions to be able to measure that. And after the Rosetta mission to Comet 67P, more or less that confirmed all the things we'd been assuming, that they really do seem to be low density, and they have very little internal strength. But this is still a very sparse diagram. We'd love to fill this in with more objects. And the difficulty on that is that when comets are brightest, when they're close to the sun, you really can't measure the rotation period except by using this morphology technique. So that's the reason why I'm harping on it, is that the more standard way of using a light curve, you just can't do, because the nucleus itself is so small, so faint underneath all the bright gas and dust that it's difficult to do. And the other thing is that if you were to use Hubble or James Webb for it, which they are probably capable of doing this for a lot more comets than we've used them for, the problem is they just take a tremendous amount of time, and it's it's not in the best interest of the whole community to devote all that time to one small comet when you could be spending it on many other exciting discoveries. Something else that's come out of this in the last decade or so has been that some comets have changes in their rotation periods. And again, that was something that wasn't a surprise. We know comets are outgassing, and they're from your basic physics, there should be a torque involved. You'd expect that to change the rotation period, either faster or slower. But it took a long time to be able to detect it because, again, you need a whole lot of data. I've been involved in many of the data points that are on this plot, which is all of them that are known. And they were things that either took a very weakly active comet using the photometry technique when it was far from the sun, just because it happened to be large and not very active, but it took decades of observations. So people 30 years earlier had collected data that I relied on, and then I collected new data, I and my collaborators, and we measured a change, a very small change. Or what we've seen is several cases of very dramatic changes, just within a few weeks, having a period change from, say, 17 hours to 18 hours. And that was surprising, but that came about, again, just entirely from morphology. And so these changes in period have led astronomers to come up with some additional insights into what might be going on at the nucleus, at the level that we can't otherwise see unless we send a mission there. And I'll just note that from my own work and mine with my collaborators, we've now been doing imaging for about 20 years using modern CCD cameras. So taking digital pictures rather than the old style of taking glass plates or maybe using a photo multiplier tube where you effectively only have a single pixel. So we have 20 years or so of fairly comprehensive observations of comets using these narrowband filters. And so one of the things I've been doing at the Naval Academy is getting some of my better students to start digging through my archive of about 75 comets and starting to try and do some classification to see if we can come up with some what I call population level studies of the morphology. And there are just so few comets that have been studied in detail morphologically like this that I think I'm hopeful that it's going to lead to some interesting results, although I don't have anything to report quite yet on that. So that brings me up to what I'm calling recent and future advances. The first thing is to talk a little bit about the filters themselves. So I mentioned a little while ago that the original filters were made in the 1990s. They were distributed, NASA funded it, they were distributed around the country to various private facilities, but most of them were too small to work with modern CCD cameras. So in the 90s, what cameras existed were quite a bit smaller, and they were largely being deployed with photomultiplier tubes as well. So I was fortunate enough to get an early career fellowship from NASA, which allowed me to propose something ideally that would be beneficial to the community and not just myself. And I proposed to try and build some new filters, to update those filters. And I had enough funding to buy a few sets of CN filters after doing some testing in various ways, as well as some OH filters and some what we call blue continuum filters, which is not the whole set. The whole set has 11, but it was just they're very expensive to build. So I focused on the ones that had resulted in the most reliable science, which were those filters there. And as I'll talk about in a moment, I've been able to get them out to a number of observatories around the world to make them more accessible to both myself and to others. One nice thing was that technology has improved in the last 30 years, and so the throughput from those filters is improved. Although I will say that there were aspects of the technology in the 90s that actually worked better for this process, and some of the people at the Asahi in particular initially said we can't do this anymore, but then they got interested and they put a bunch of time in and they said, okay, we found a way. It just made it more expensive. So that was a lot of fun to have a company really get excited and dig in and see what they could do to help us improve things. So as of 2024, this is a map of effectively all of the existing HB filters from the 90s that were available. So they were available at Flagstaff, Arizona, which is the star in the United States, which is where I used to work and where I continue to collaborate. So I had access to them, but they were not publicly available. Then there was a publicly available set that was down in Chile. I was actually there because I got it. I asked them to move it there because it was sitting unused at Kitt Peak, and Kitt Peak in Arizona didn't have any facility that could handle them. So they moved them to Chile, and I and a few of the others have used them the last few years. And then there's a set that's privately owned in Morocco, and I collaborate with them, but I don't have direct access to it, nor does the community. So after I was able to get my filters built, and I also shared the specs with a collaborator in Edinburgh, she also bought a couple and helped get these distributed. The blue circles now show all the places that have these filters, and most of them are with this thing called the Las Cumbres Observatory, which is where I got the graphic from, at their various facilities. And Las Cumbres is a private observatory, but their time is available publicly. So any astronomers around the world can apply for time on them. And they're generally small telescopes. These are all deployed on 1 meter telescopes. But one of the things that's very exciting is that now with this distribution around the world, theoretically, I could observe, or anyone could observe a particular comet continuously for around-the-clock coverage. And my first proof of concept on this will hopefully start getting data in a week. There's a bright comet that's just emerging from the sun, 2024 E1 Virchow. I have trouble pronouncing the name. But I was allocated 30 minutes a night for a month to use these CN filters at the various LCO facilities around the world. I'll also note there's now a circle there in Maryland at the Naval Academy. We have filters permanently in use there, which one of the things that I've been trying to do is to get publishable data being done by midshipmen right here in Maryland. So I'm very pleased with this. I'm looking forward to, I hope, giving a presentation this summer to the community to make people more aware that these filters are now out there and available for widespread use. Some other advances, the real other breakthrough is this idea called an integral field unit, or IFU. And I am not much involved in this, but I collaborate with people who do. And the idea is that with modern computational power, we're now able to take a spectrum every pixel in an image. Now, the pixels have to be a bit larger than we're normally used to. But once you get over that, what you have is the ability to make an image at whatever wavelength you want, and all of those images got taken at the exact same time. The best of these is currently on the VLT, the Very Large Telescope, which is run through Europe, but it's located in Chile. And that's shown on the right-hand image here. And Apitam has been the lead on this, and I've been working with her for about a decade now, but she's had a recurring project where we've been able to get time to observe bright comets. Most recently, we did the interstellar comet 3I, which is still around, and I'm happy to talk more about that at the end if anybody wants to. But what you can do with the IFU in particular is you get these simultaneous images, and in some places you can get them, like in the bottom plot here in NH2, where the lines are so spaced out that you would never have success with the traditional narrowband filter approach like I've been talking. But with this spectroscopy approach, you can pull out enough of those lines that you can make an image and make comparisons. But the really exciting breakthrough with IFUs is with James Webb. So JWST, of course, operates in the infrared. And in particular, the NIRSPEC instrument operates where the three best ices to study for comets are: the water, the carbon dioxide, and the carbon monoxide. And we now have the ability to make IFU images, in other words, a spectrum at every pixel images of water, CO, and CO2, as well as the other species that are around in these regions as well. So I think this is really going to be exciting in the next decade as JWST continues to operate. The one downside, though, is that it is very restricted in where it can point. It can't point too close to the sun. It can't move too quickly. And so the times when comets are the brightest, they are very hard for JWST to actually do. So they have made some fantastic results at larger distances from the sun. They haven't yet had that breakthrough observation of a comet near 1 AU. Just because of logistics. And we haven't had a particularly bright comet that fit since they've been flying. But one result from JWST that I am very excited about is shown here. This is from a paper by Sarah Faggi, who works at NASA Goddard, from a couple of years ago of Comet 29P. So 29P orbits out near Jupiter, so it never comes in very close to the sun. But JWST has such great resolution that they could zoom way in that central part. Every pixel in these two pictures on the left are probably within the single pixel I would take from the ground. So just phenomenal resolution of what's happening. And what they found was that the carbon dioxide, which is the top panel over there on the left, and the carbon monoxide on the lower panel were not distributed the same. So the yellow points here are the brighter spots, and in the CO2, you see that there's a jet up and a jet down. And the CO, you only see a jet up. And so the thought there is that this is probably telling us about the conditions when the comet formed, that those ices probably were either formed, parts of it were formed in different places, or there was some different level of mixing in different parts of the comet. So some parts got both CO2 and CO, other parts maybe only got CO. Now there are counter arguments. This may be that there's been some evolution of the comet over time due to heating on one side versus the other side, or fallback of material. We can get into lots of ways this might be different, but this is just a really exciting result. And what I'm really looking forward to is when they can do this on one of these comets that's near 1 AU, when I or collaborators are also able to get imaging through the traditional ground-based narrowband imaging and compare those images and overlay where does the CO2 or the CO or the water look, and what does the CN or this OH or the C2 look. And then we can really hope to start finding these relationships between which ices live together in the nucleus of a comet, again, trying to inform our models of the protoplanetary disk where they formed. Now, one thing that if you've been following astronomy news, you're probably aware of is that the Rubin Observatory is about to begin observing, hopefully by the end of the month, maybe early March, but it's very, very close. They're just ironing out the final details. So I am excited about it as an astronomer, but for the case that I've been talking about now of doing these narrowband observing, it's probably not going to help much. LSST is going to find very, very faint things that are never, or are not likely to become as bright as what I need for my studies with this. And furthermore, if they were going to get that bright, they would have inevitably been discovered anyway by some other survey. Just we'd learned about them later without Rubin. So it'll be an amazing advancement, not necessarily so helpful for what I'm talking about right now. All right, so let me grab a drink of water and then I'll finish off. So my last little bit here was to hopefully at this point you're excited about what I'm talking about and thinking maybe I could do something like this. So first thing I want to say is we can do this here. As I've mentioned, I've been successfully getting data for the occasional bright comet from the Naval Academy from Annapolis, Maryland. So here's a proof of concept here, and the 4 images of this bright comet. And I showed this image earlier when I was showing the modeling enhancement process. But the one that looks crooked, we actually took from Annapolis. The 3 that look normal were all taken in Arizona, and they're better quality. It's a bigger telescope. It's a 1 meter. Here we're using a 20-inch. It's at 7,000 feet elevation. We're at sea level. But the point is that what we took helped. That this comet was only visible for 30 minutes or an hour per day. So we could never get enough data from Flagstaff alone to measure the rotation period. But getting additional data from Annapolis from about 3 hours different did allow us, it filled in the gaps of missing times and helped us to figure out what the rotation period was of this comet. So I was able to get a publication that included 4 of my midshipmen, including the one who's shown here in this picture. Which I was just really excited about because this is the first time I had something published using the students, and to my knowledge, the first publication using the on-campus facilities we had at the Naval Academy for published astronomy work. So if you're thinking about getting the filters, first thing I want to say is that the ones that I'm using, these professional grade ones, are quite expensive. So I've been buying 50 by 50 millimeter square images that run square filters, excuse me. They run about $5,000 per filter. The number's a little bit fuzzy because I've bought them in different quantities and they've also, these have been over the last several years, so prices may have fluctuated. But what I want to say is that there's a more accessible alternative. It doesn't perform quite as well, but they are a whole lot cheaper. So that second bullet point there mentions the company is called Semrock. It's the specific filter that matches the CN, which is the one that has had the best results, is about twice as wide. It's an 11 nanometer wide filter, whereas the professional grade ones I have is a 6 nanometer wide. So by being wider, it lets in additional wavelengths, which are not generally as interesting to us. But what is interesting is that you can still do very nice science with it, and they're a whole lot cheaper. So I looked yesterday, and at through the US-based reseller of them, they were selling a 25 millimeter diameter for $375. And I know an astronomer, an amateur astronomer in Finland who's been using these. So Jorma Riska, who I've quoted that the figure is from him, and I've given the quote for the talk he gave last year at a meeting, has been using these for about a decade. He's actually the one who told me about them. And he has his own facility in Finland, and he also has one, I want to say, in North Africa as well, that he uses remotely. And he uses these filters. And from time to time, a comet gets bright enough that he's able to do, and he'll send me his images, and I'll compare them with what we're getting using the filters out in Arizona, and they look very nice. So this absolutely can work. You just got to pick your spots for doing it. And then the last thing I want to say is that there's this, what I would call the do-it-yourself approach, that if you already have some broadband filters, and in particular, if you've got the Sloan G and R filters, or an equivalent like a V and R filter, with a little bit of computational savvy, and certainly what I saw before I started speaking tells me that some of you members certainly do, you can take a G image, which is on this image is on the left-hand column, subtract an R image, which is the second column, and if you scale them appropriately, as showed in the third image, you can essentially remove all of the dust, and what's left over is the gas that's in that G-band image. So the proof of concept that I showed here, we published in a paper in 2022. And that third column shows the difference, and the bottom row is the enhanced version, where it's much easier to see the gases, the jets. So this has sort of, in the yellow is the bright here, sort of diagonally up to the upper left and to the lower right appears to be two jets. And I deliberately took images at almost the exact same time using the CN filter at Lowell Observatory, and that's that far right column. And you see they look very similar. It turns out that the G minus R isn't actually CN, it's C2, so diatomic carbon. But I have shown over the years that C2 and CN almost always have very similar spatial distributions. So this similarity here, I have very high confidence that the technique is working. And so this is something I'm hoping to be able to use with LSST. So as I mentioned, it's going to be getting, it's not going to be so great for most of what I want to do, but it will get GNR filter images many times on the same night. And so I'm hoping that I can do something like this and hack it to get it to give me a quasi-gas image here. So with my last slide is just to say, if you're excited about doing this and you want to look into it more, the first thing you want to think about is how bright is the comet. Absolutely, it needs to be brighter than 10th magnitude, and almost certainly if you're using smaller telescopes and you're doing it from the DC suburbs, you want brighter than that. Something like 5th magnitude or so, I would say, is probably the starting point. A good place to look to figure out what's available is this Seiichi Yoshida's website, which I've taken a screenshot from it here. And what he does is he classifies by the hemisphere and then by month, and then he just lists comets by brightness. So I pulled this yesterday. You can see in the pink here is the February 2026 from the Northern Hemisphere. So at the start of the night, for instance, is this comet I mentioned that I'm trying to do next week with around-the-clock coverage, 2024 E1, and that's going to be magnitude 7, and it's an evening object. So you can patrol this website, look for opportunities, or if you hear about it in the news about a bright comet, check it out on this website to confirm. I would also say look for objects that are at or inside of 1 AU, where they're likely to have the best gases and most active. And then the real sweet spot for amateurs to contribute is to look at low solar elongations. So as you're likely aware, most professional observatories will not point close to the sun. A few places will let you go inside of 50 degrees or so, but many of them won't. So that's the sort of sweet spot for people who are wanting to do something that professionals are probably not able to do. So if you go after those comets that are, say, only 30 degrees solar elongation, you're going to potentially be able to get data that is of use to the community and that nobody else is getting. So that is my last bit on this, and at that point I'll wrap it up and take questions.
Any questions? Just be sure to unmute, or you can post them in the chat thing. Either way.
Dr. Knight, can I ask you a question? If you were on the surface of a comet, what would the gas jets look like?
Yeah, that's a great question. It turns out that they're very diffuse. So when the Rosetta mission was at the Comet 67P, they were orbiting just tens of kilometers off the surface, and they rarely saw these jets. We could deduce, we could see them from the ground, but they could not see the gas jets up close. They could see the dust jets, but even those didn't look like what we see from Earth. So I think it actually takes a good bit of optical depth, so a lot of material along your line of sight before you start to notice it. And if you're too close, if you're in the middle of it, it's just any one line of sight has too few molecules that you wouldn't really even notice them.
Any other questions? Yeah, George?
I believe I saw there are images of Hale-Bopp's nucleus that show rotation. You can see this without any filter, can't you, in dust or gas?
So, right. So Hale-Bopp, we didn't get an image of the nucleus, but we certainly have images that showed the rotation. And that one was pretty unique. That's the only comet I'm aware of where the dust was yielded the rotation period out of it. Otherwise, we've not been successful with getting it from the dust. And I think it's just because Hale-Bopp was incredibly dusty. It had a huge level of activity, much higher than pretty much any other comet. And it seems to have been a very unusual object. And the things we learned with Hale-Bopp, it turns out, haven't been applicable to pretty much anything else in the last 30 years.
I used a 10-inch telescope observing Hale-Bopp, and I think I did see these jets. Mm-hmm. And I think there was a guy that took pictures of them, CCD pictures. I think he probably was an amateur, and I have them, but I've seen very little about the rotation of Hale-Bopp. Everyone had all these pictures of the tail. But in fact, the nucleus is quite interesting. It was very interesting.
Yeah, Hale-Bopp as a comet was just incredible. It was a huge nucleus. I was in college at the time, so I was not yet a professional astronomer, and I wish I had been paying more attention. But just a massive nucleus. It was so bright that we could do it very well at sort of any wavelength you wanted, even though it was only visible at near the horizon for a short bit of time each night. Must have been amazing to get to study.
What about the Japanese one right before Hale-Bopp?
Hyakutake.
Yes.
Yep. Yeah. Also amazing. Both of those have had a wealth of papers. Hale-Bopp has many more, but Hyakutake produced a number of really fantastic papers as well.
And then there was the one, the Holmes, Comet Holmes. It just blew up.
Yeah. I remember seeing that from my parking lot in the University of Maryland with the lights on. I could see it. And for those of you who aren't familiar, Comet Holmes just exploded one night. The comet is still there, but it had a massive outburst. It brightened by, I want to say, 10 or 12 magnitudes.
Any other questions that we have for Matthew? Matthew, this was super interesting. We really appreciate the time and the knowledge that you shared with us, and we'd like to have you back sometime in the future if you're interested, and come visit us if you're in the area. We would love to have you in a meeting.
Yeah, thanks. Okay. I'd be happy to.
Okay, and best wishes to you and your students and your research, and we thank you again for the time that you've given us.
Yeah, thanks for having me.
Okay, folks, this will conclude our meeting, and those of you headed to the Super Bowl stuff, be safe and enjoy the game, and the others and enjoy the peace and quiet. Okay, and we all hope for the snow to go away.
Thanks a lot, Matthew. Great talk.
Yeah, thank you very much. It was great.